Good day. My name is Giancarlo Sanchez, and I'm a software engineer. Today, I'll be exploring why unguided processes cannot build Google or DNA through a thought experiment. We will bridge biology and technology to highlight how randomness alone cannot account for the complex functional systems we see in life's ultimate software, DNA. Here is the big question. Is life the product of random chance, or does it point to a masterful design? Darwinian evolution provides a mechanism, natural selection and random mutations, that could explain how complex structures like the eye or wings could arise through gradual step by step processes over long periods of time without requiring a designer. Evolutionary biologist Richard Dawkins, in his book The Blind Watchmaker, claimed that Darwin made it possible to be an intellectually fulfilled atheist. Intelligent design, however, still insists that the complexity and functionality of living organisms are evidence of an intelligent mind, and that Darwinian evolution mechanisms are insufficient to account for the specified complexity of information in existing life forms, invalidating Dawkins' claims. This presentation aims to support the intelligent design argument from a bottoms up approach through a thought experiment, using software engineering concepts and practices. While this presentation is technical, I'll try to simplify the concepts for the broader audience. Let's dive in. Let's start with a simple analogy. DNA is often referred to as life's code because, like software, it stores, processes, and executes instructions. Each base pair in DNA can be compared to a line of code in a program. In both cases, these sequences must be precisely structured to function correctly. For example, a single error in your program can crash your application, just as a mutation in a DNA can disrupt critical biological processes. This analogy lays the foundation for understanding the parallels between biology and technology. DNA and software systems like Google Maps share a vast array of traits and features. They both are written in a language. Google Maps operates binary, zeros and ones, while DNA uses a four-letter code, A, T, G, and C, which are chemical bases. They both store large amount of information. Google Maps stores vast amount of geospatial data, while DNA holds all the instructions for building and maintaining life. Both are executed and have a runtime environment. In Google Maps, code runs on hardware, such as servers in a data center. For DNA, cellular machinery reads the genetic code to perform its functions. They are highly resilient. Google Maps adapts to changes on the roads and is able to recommend you optimal routes regardless of traffic conditions, unexpected accidents, and road closures. When DNA copies itself, random errors can occur during copy because sometimes the copying machine, a special protein called DNA polymerase, picks the wrong letter, A, T, C, or G, to match, like putting the wrong puzzle piece in a place. However, DNA polymerase checks each letter it adds, and if it makes a mistake, it erases it and tries again to get it right. They are both functional and task oriented. First, think about how Google Maps works. It provides step by step directions to guide you to your destination. Similarly, DNA provides precise instructions to build proteins, which are like the tools and workers your body needs to function. Now, let's look at the outcomes. When you follow Google Maps, you take actions like turning left or right, so you can reach your destination. DNA works in the same way. Its instructions are followed to create proteins like insulin, which actively helps your body moving sugar from blood to the cell, where it is used for energy. Without insulin, blood sugar levels would rise too high, which is dangerous. Finally, the purpose. Google Maps ensures you get where you need to go. DNA ensures your body stays healthy by producing essential proteins like insulin, which regulate blood sugar, or enzymes that drive chemical reactions to keep you alive. So, in short, Google Maps is a guide for navigation, and DNA is a guide for life itself, providing the instructions to keep everything running smoothly. They are both modular in nature. In software engineering, the same code segments can be used across different programs to save time and ensure reliability. For example, a library that formats dates might be used in Google Maps to display travel times and in Weather app to show forecasts. Similarly, DNA operates with a similar kind of modularity. The same genetic sequences or code can be found across different species. For example, the genes responsible for basic processes like cell replication or energy production are highly conserved and appear in both bananas and humans. This reuse of genetic modules highlight the nature of efficiency and adaptability, just as software engineers use reusable code to build robust, complex systems. Another set of parallels reveals the sophistication of both systems. They can be hacked. Just as Google Maps can be modified by developers, DNA can be edited through genetic engineering. But modifying either system requires understanding its design. Backups are a must for reliability. Google Maps uses redundant servers to prevent data loss, while DNA stores paired chromosomes as backup mechanism. With regards to optimization, DNA is a clear winner. While software like Google Maps compresses data for efficiency and optimizes code for performance while navigating, DNA fits billions of base pairs into microscopic chromosomes that are able to orchestrate all of our biological tasks for living. Richard Dawkins, an evolutionary biologist and leader of the New Atheist movement, says that machine code of the genes is uncannily computer like. Bill Gates also agrees. DNA is like a computer program, but far, far more advanced than any software ever created. And Craig Venter, leader of the Human Genome Project, says that life is a DNA software system. Some may argue that comparing DNA to software is misleading because biological systems evolve and adapt, while software is static and designed. However, the analogy between DNA and software is not about their ability to evolve, but about their shared reliance on coded information. DNA stores, processes, and executes instructions in a way that is fundamentally similar to computer programs. Both require precise arrangements to function. Furthermore, DNA shows signs of optimization, which involves improving a system based on specific criteria, such as efficiency, functionality, or precision. Without a purpose, there is no criteria to guide or measure improvement. Random processes may produce changes, but these changes are not inherently directed towards a beneficial or functional outcome. To appreciate the complexity of DNA, let's compare it to software. A simple game like Pac-Man has about 1,000 lines of code. An E. coli bacteria's DNA has 4 million base pairs. All of Google's services, one of the most complex human software ecosystems, has 2 billion lines of code. Human DNA, a staggering 3 billion base pairs. So here is our hypothesis. If an unguided process cannot create a working software program, then an unguided process cannot explain the precise design of DNA for life. But what about if someone argues that natural selection is not random? It is a guided process that can create complexity over time. For natural selection to act, there must be an already existing population of replicating entities, with variations to select from. However, the machinery required for replication, such as proteins, enzymes, RNA, or DNA, is itself complex and unlikely to arise by chance. This creates a chicken and an egg problem. The replication machinery depends on pre-existing information encoded in DNA or RNA, but that information cannot arise or be maintained without replication. Now, while natural selection itself isn't random, it depends exclusively on random mutations to provide the raw material for new features in evolution. Here's where the challenge comes in. Can these random mutations account for all the new information developed all the way back from our unicellular common ancestors down to us? The transition from simple life forms to human evolution will need to generate vast amounts of genetic information for novel structures like brains, limbs, and immune system. Mutations primarily shuffle, duplicate, or modify existing genetic material. They don't reliably produce new sequences of functional specificity. Most random mutations are either neutral, which have no effect, or harmful, which damage existing functions. Beneficial mutations that improve functions are extremely rare. Think of it like randomly editing the lines of code of a computer program, where most of the changes will probably break it, that rather than add features. Dr. William Dembski is a mathematician, philosopher, and pioneer in intelligent design theory. He is known for developing the explanatory filter and publishing extensively on design detection and specified complexity. He developed the explanatory filter to explain the origin of things. Three categories reflect the major modes of causation recognized in science and philosophy: deterministic processes, such as natural laws; randomness, chance; and intentionality, design. No phenomena currently require a fourth category. The filter has been successfully applied to distinguish between natural and artificial causes in fields like archaeology, where identifying a natural formation from a man-made artifact is used for, and cryptography, detecting intentional patterns. Critics, especially from the evolutionary biology community, argue that natural selection combines chance and law, making design unnecessary. However, the explanatory filter remains robust because all known causes of phenomena can be classified into natural law, chance, or design. Proposed alternatives either fit within these categories or fail to provide a distinctive explanatory mechanism. As such, the filter is comprehensive for evaluating the origin of complex specified systems like DNA. Émile Borel was a renowned French mathematician and probabilist who pioneered modern probability theory. His work on measure theory and threshold for practical impossibility remains foundational in science and mathematics. He proposed a threshold for practical impossibility, 10 to the minus 50. Events with probabilities below this threshold are so unlikely that they effectively cannot occur within the physical universe. Events with probabilities lower than this threshold cannot happen within the finite universe. For example, getting struck by lightning 10 to the minus 6, which is to say 1 in a million, or winning the lottery by guessing a 6 number draw, is 10 to the minus 7, which is equivalent to 1 in 10 million. Solving a Rubik's Cube by randomly moving faces 10 to the minus 19. While highly improbable, these events can happen. However, others, such as finding a particular grain of sand on Earth, or brute forcing a 256 security encryption key, or generating all the information bearing infrastructure in the precise sequence to generate an E. coli bacteria 4 million base pairs DNA, are mathematically impossible, even if all the particles in the universe since the beginning of time were involved in the process. There is just not enough possible events for them to happen. For the bacteria, it involves building amino acids that build into proteins that are encoded into DNA that form a genome. There is an exponential complexity that we will illustrate in the next slide. But why consider this threshold? Borel's threshold is widely respected in probability theory because it contextualizes probabilities beyond human intuition. It establishes a practical guideline for distinguishing between improbable but possible events and events that exceed the scope of physical reality. Emil Borel's threshold is a scientifically valid tool for distinguishing possible events from those that exceed the universe's capabilities. If events below 10 to the minus 50 are deemed practically impossible, then the chance-based origin of DNA, with probabilities far exceeding this limit, strongly support the need for a guiding intelligence. This chart includes two lines for both complexity in blue and improbability in red, along with Borel's threshold, the green dashed lines on top, for impractical possibility. In our x-axis, we can see the stages of DNA formation. It tracks the progression from amino acid formation to a full E. coli genome. In our left y-axis, represents the increasing complexity of each stage, with higher values indicating more intricate structures. In our right axis, it shows the decreasing likelihood of achieving each stage through random processes, with lower values or more negative indicating extreme improbability. Anything falling below the green threshold line is in the domain of practical impossibility. So, mathematically speaking, only the generation of amino acids from unguided processes is possible. The follow-up generation of proteins down to the genome are mathematically impossible. But what about when people say, well, the impossibility arguments are flawed because highly improbable events happen all the time? While improbable events can occur, the key distinction is between plausible improbabilities, like winning the lottery, and practical impossibilities, such as generating functional DNA through random processes. Let's put randomness to the test. Here's a simple Python program. Print welcome to the matrix. It has 26 characters chosen from an ASCII set of 128 possible symbols. The probability of randomly generating this code is 10 to the minus 52, already beyond Borel's threshold. This is a sample program that randomly tries to generate our program print welcome to the matrix from before by changing characters on a string. If we let this random typing program run forever, it still would not generate our basic application, much less a functional code base like Google Maps or DNA. Random processes don't create order or functionality, they produce chaos. This visual emphasizes the futility of attributing DNA's complexity to randomness. If we let this video run forever, it will never finish, so we'll just skip ahead. What are the implications? DNA works like computer software. It stores, processes, and executes precise instructions. Randomness cannot create software. Even small programs are impossible to generate through random typing. Randomness cannot create DNA. The complexity and functionality of DNA requires intentional design. Ask yourself, if we cannot create randomly a simple line of code that performs a specific function because it is mathematically impossible, how can still we argue that it would be possible to randomly generate Google's 2 billion lines of code, let alone the 3 billion base pairs in DNA? It is clear that unguided processes are insufficient to produce such large yet specific information systems. Thank you for your attention. If you'd like to learn more, join me in conversation and visit the Apologetic Network. And let's continue exploring the evidence for design in nature and engage with others in meaningful discussions. Feel free to scan the QR code to connect with me and the rest of the team.